Welcome to this lecture on rules of inference for predicate logic. Notice in the previous lecture, all the rules of inference that we introduced applied only to propositional variables, or propositions. They did not involve predicates, variables, or quantifiers. So in this lecture, we're going to solve this problem. We're going to introduce rules of inference that will allow us to make arguments in predicate logic. In particular, these rules of inference are going to deal with quantifiers. So the first rule of inference is called universal instantiation. From the name, we can infer two things. First of all, it's going to involve the universal quantifier. And by instantiation, we mean going from the general to the specific, to the instance. So this is going to be a rule that allows us to start with a universal quantifier and then to drop it to make a specific inference from a general statement. So here is the rule called universal instantiation. Only one premise, it says, for all x, p of x. Well, if that is true, the rule says you can infer p of c. Notice we drop the quantifier and we introduce a constant c instead of the variable x. So what is C? C is any specific member of the universe for the variable x. This rule, I think, makes sense intuitively. What it says is, if you have established already that P of x is true for every single element in the universe for x, then clearly P must be true for any element in the universe. Since we don't know which one in particular, we just call it C here. But in a proof, you would be able to choose any specific element in the universe that is useful to reaching the conclusion you are after. The second rule of inference you need to learn is called universal generalization. It's essentially the reverse of the first rule. That is, instead of dropping a universal quantifier, it will allow you to introduce a universal quantifier. In other words, it generalizes from a specific proposition to a general proposition that has a universal quantifier in it. So this rule, again, only has one premise, namely P of C bar, where C bar is an arbitrary element of the universe. And what this rule says is that from P of C bar being true, you can infer that for all x, P of x is true. Again, let's define what C bar is. It's an arbitrary member of U, the universe, for the variable x that shows up in the conclusion here. Now, this rule is not at all as intuitive as the first one. In fact, it should give you pause. Because what it says is, from a single instance of the property P, say P of C bar, it allows you to infer a much more general statement, namely P of x is true for every single x in the universe. Now, how could this be? Well, it turns out this rule is used quite a bit in mathematics, and we will use it quite a bit in the rest of the course when we write proofs. And here is why it works. The key word here is that C bar is arbitrary. In other words, yes, C bar is a unique element, it's a single element of the universe, but it's an arbitrary one. It's one you could have chosen randomly. You don't know which one it is, it could be anyone. In other words, in mathematics, we always or very often start proof like this. You say, let C bar be an arbitrary integer. So all we know is that C bar is an integer. In other words, it could be any integer. And if from that assumption, we can prove some property P of that integer. For example, we could prove that C bar is either a prime number or a composite number. Because we were able to prove that property P of C bar without making any special assumptions about C bar other than it's just an arbitrary or random integer. Because of that, we are allowed to infer that property P must be true for all the integers because it's true for any arbitrary or unknown integer And that is the meaning of this universal generalization rule. I strongly encourage you to think about this rule and make sure you remember to go back to it when we use it later in the course. Our third new rule of inference is called existential instantiation. So the name tells you that it will involve an existential quantifier, and instantiation tells you that it's going to allow you to drop the quantifier, the same way that this first rule allowed you to drop the universal quantifier. So the premise of this rule is there exists x, p of x. And what the rule says you can infer from that one proposition is that p must be true for some element c of the universe. I think this is intuitive. If there exists x such that p of x is true, it means there exists at least one element in the universe for which p is true. Now we don't know what that element is. That's the crux. So we just give it an arbitrary name like the constant c. But because we don't know what element, specific element of the universe has the property p, you can't just pick any name that will allow you to conclude the proof. The crucial constraint here is that the name c must be chosen such that it's a new name in the proof. In other words, c should have never appeared in the proof up to that point. It's an unknown element of the universe, and it cannot be one of the elements of the universe that you have referred to earlier in the proof. We'll get back to this in a later segment of this lecture. Now, if you figured out that there must be another rule based on the symmetry of the name for the three previous rules, well, you are correct. There's one more new inference rule for predicate logic, and it's called existential generalization. As you can imagine, it allows you to introduce or to generalize from a specific proposition to a quantified proposition where the quantifier will be an existential one. So there's only one premise again in this rule, and it's p of c. From that, the rule allows you to infer that there must exist some x such that p of x. And here, like in the first rule, c is any specific member of the universe for the variable x. In other words, c is a constant. It's the name for a specific instance of the universe. And clearly, if the property p holds for c, where c is a member of the universe, then it must be the case that there is at least one element in the universe for which p holds. Well, that element is c. So this rule is as intuitive as this one. So in conclusion, notice that we have four rules, 2 for the universal quantifier and 2 for the existential quantifier, and for each quantifier, one rule allows you to drop it and another rule allows you to introduce it. So this concludes this first segment. In the next two segments, we're going to look at a couple examples of proofs in predicate logic that will illustrate the use of some of these inference rules.